Okay, now let us start with the RIPng for IPv6. RIP, or Routing Information Protocol, is the oldest of the distance vector routing protocols, but it is still in use. Although RIP lacks the sophistication of more advanced routing protocols, its simplicity and continued use are an evidence of its functionality or in the current networks. There is an IPv6 form of RIP called RIPng. ng is a shortcut for next generation. RIP was invented in 1988, and since then RIP has been updated, including the RIPv2 in 1998 and then RIPng in 1997. Routing Information Protocol Next Generation, or RIP for IPv6, functions the same and offers the same benefits as RIPv4 in IPv4. Just like RIP for IPv4, it uses hop count as the metric. Hop count means the number of routers to reach the destination. It sends updates every 30 seconds because it is dynamic, so it is adapted to the changes. It checks the situation around and change update to other routers to monitor any changes in the topology. And also RIPng messages use the UDP, but yes, in the same port actually, which is 521, and the multicast address in IPv6 is FF02:9. Okay. Now we want to compare the RIPv4 with RIPng. As we say, RIPng is very similar to RIPv4 in both its operation and configuration. But there is some, difference between these two protocols. In terms of advertised route, of course, RIPv4 advertises IPv4 route, while RIPng advertises routes for IPv6 routing table to be populated in the IPv6 routing tables. In terms of distance vector, RIPv2 and RIPng are both distance vector protocol that apply the a special kind of algorithm to do this function, and the algorithm is called Bellman-Ford algorithm. In terms of the metric used, RIPv2 and RIPng both use a metric between 1 and 16, representing the hop count, As we said, hub count means the number of routers to reach the destination. We call it hub count. And the maximum hub count is 15. In terms of routing table metric, in RIPv2 and of course RIPv1, the metric received in the routing update is the metric the receiving router uses in its routing table for that network. So there is nothing, done as a router, just need to receive this update and save it. But in a Cisco implementation of RIPng, the same metric is sent, but it is incremented by the router receiving the update. So in RIPng, the receiving router will increment the metric and save it in its routing table. This is, a big difference between RIPv2 and RIPng. And for the UDP protocol, both routing protocol, RIPv2 and RIPng use the UDP protocol, but the RIPv2 uses port number 520, while the RIPng uses UDP port 521. Okay. In terms of update, RIPv2 and RIPng both send periodic updates every 30 seconds. And for the timers, RIPv2 and RIPng both use hold down and other timers to help prevent routing loops, which is very good feature actually in the routing. Split horizon or split horizon with poison reverse are used with both RIPv2 and RIPng, and this feature helps prevent routing loops. In terms of source and destination address, RIPv2 sends messages to the IPv4 multicast address, which is 224.0.0.9, and this message uses the source IP address of the exit interface. So from the exit interface, the updates will be broadcast to multicast address, which is this address in case of RIPv2, while in RIPng the messages sent to the multicast address, which is FF02::9, and the source address is the source of the link local address actually of the exit interface. Okay, in terms of authentication, RIPv2 use either plain text or message digest 5 or MD5, while RIPng does not include its own authentication mechanism, and the authentication are provided by the standard IPsec, IB security protocol, which is defined in the IPsec protocol for IPv6. Okay, now for the EIGRP for IPv6, we will explain, then we will do a comparison between IPv4 and IPv6. Enhanced Interior Gateway Routing Protocol is a distance vector. Okay, it is an enhancement of IGRP, Interior Routing Protocol, and both of them are Cisco copyrighted protocols and only operate on Cisco routers. Unique to EIGRP is its reliable transport protocol, RTP. This is important because it provides reliable and unreliable delivery of EIGRP packet. In addition, EIGRP establishes relationships with directly connected routers that are also enabled for EIGRP. We call this relationship as NIPer relationships. NIPer relationships are used to track the status of these neighbors. RTP and the tracking of NIPer adjacencies set the diffusing update algorithm, DUAL for short, and this algorithm is a unique algorithm to EIGRP. It resides at the center of the routing protocol, and it guarantees loop-free path and backup path through the routing domain. Also, duals select the primary route to install in the routing table, which is known as successor, and also it maintains a list of guaranteed loop-free backup route, and this route known as feasible successors. So it maintains successor, which is the main or the primary route, and it also maintains a list of guaranteed loop-free route, and it these routes are called feasible successors. Okay, EIGRP, IPv4 runs over IPv4 network layer, communicating over with other EIGRP v4 peers, while the EIGRP for IPv6 has the same functionality, but it uses the IPv6 as the network layer transport to communicate with EIGRP IPv6 peers. This communication is very important because it uses it used to advertise the changes in the route between the NIPer routers. Okay. Now we will do a comparison between EIGRP for IPv4 and EIGRP for IPv6. IPv6. In terms of advertised route, EIGRP for IPv4 advertised IPv4 route, while the other one, the EIGRP for IPv6, advertises the route to be populated in the IPv6 routing table. In terms of distance vector, both of them are distance vector, and in terms of convergence technology, EIGRP for IPv4 and for IPv6 both use the dual algorithm. This represents the same techniques and process, including successor and feasible successor. And in terms of metric, both of them use bandwidth, delay, and reliability, and the load for their composite metric. Only bandwidth and delay are used by default, and you can use, reliability and load if you want more metrics. In terms of transport protocol, both of them use the RTP, which is responsible for guarantee and order the delivery of EIGRP packets to all neighbors for both protocols. Okay, so as you see, there is no big difference between them so far. In terms of partial updates, both send incremental updates when the state of destination changes, instead of sending periodic updates of the entire content of the routing table. So no need to send periodic updates. In case of any change, the EIGRP for IPv4 and IPv6 send the incremental updates. In terms of neighbor discovery mechanism, both of them use a simple hello mechanism to learn about neighboring routers and to form the adjacencies. In terms of source and destination addresses, EIGRP for IPv4 sends messages to the IPv4 multicast address, which is 224.0.0.10, and the source address is the address of the exit interface. And for the EIGRP for IPv6, this protocol will send the messages to the IPv6 multicast address, which is FF02:10, which includes all the EIGRP routers in the link, in the same link, and the source address for the messages is the link local address of the exit interface. In terms of authentication, both of them use the MD5 authentication, and in terms of the router ID, router ID, both of them use a 32-bit number for the router ID. This 32-bit router ID is represented in dotted decimal notation and is commonly an IPv4 address. Okay, now for the last protocol, which is OSPFv3 for IPv6. This protocol is a link state classless routing protocol that uses the areas concept for scalability. In 1991, OSPFv2 was introduced to offer significant technical improvements over its successor, which was OSPFv1. In 1999, OSPFv3 for IPv6 was published. Let us, to explain it, we want to think of a link as being an interface on a network device. So OSPFv3 protocol makes its routing decision based on the state of the links that connect source and destination machines. The link state is a description of that interface and its relationship to its neighboring networking devices. The interface information include the IPv6 prefix of the interface, the network mask, the type of network it is connected to, and the devices connected to that network, and of course other information. This information is propagated in various types of link state advertisement, which is called LSA for short. So the LSA contains, several information about the link state, like IPv6 prefix, network mask, type of network it is connected to, the devices connected to that network, and other information. A device collection of LSA data is stored in a link state database, not routing table as in other protocols. The content of the database, the content of this database, when subjected to some algorithm, result in the creation of the OSPF routing table. The difference between the database and the routing table is that the database contains a complete connection of raw data, and the routing table contains a list of shortest paths to known destination through a specific device interface port. So we don't have in this protocol, in this dynamic routing protocol, we don't have routing table. We have something called link state database. In terms of comparing the two protocol, OSPFv2 and OSPFv3, in terms of advertised, OSPFv2 advertises IPv4 route, while OSPFv3 advertises route for IPv6. For the link state, OSPFv2 and OSPFv4 are both link state routing protocols. In terms of the metric, OSPFv2 and OSPFv3, the metric is the cumulative bandwidth of the outgoing interface to the destination network, which is 108 over the bandwidth in the and the bandwidth measured in bit per second. In terms of packet types, OSPFv3 uses the same 5 packet types as OSPFv2, which is hello, database description, link state request, link state update, link state acknowledgement. In terms of LSA flooding mechanism, the aging of the link state database as well as the flushing LSA from the routing domain through the perimeter aging process remains unchanged. Cisco routers running both of them periodically flood their link states every 30 minutes and flush LSA after 60 minutes. In terms of router ID, both of these two versions of OSPF use a 32-bit number for the router ID represented in dotted decimal notation. Okay, in terms of neighbor discovery mechanism, the neighbor state machine including the list of OSPF neighbor state and events remain unchanged. However, in OSPFv3 there is no same subnet requirement to form neighbor adjacency as in the OSPFv2. This is because neighbor adjacency are formed using link local addresses, not global unicast addresses. In terms of source destination addresses, of course the destination and sources are different. Here we have this destination for all router, and here we have this destination for the designated routers, and the source is the exit, the IPv4 of the exit interface. Here we have in OSPFv3 we have link local addresses instead of IPv4 addresses. Okay. In terms of authentication, OSPFv2 uses plain text or MD5, and OSPFv3 uses the encryption and authentication provided by IPv6. Okay, in terms of non-broadcast multi-access, which is a feature for the OSPF protocol, and also for the point to multi-point topologies such as frame relay, there is no difference between the two protocols. And in terms of areas, both of them use the concept of multiple areas. No changes between the two protocols. Okay, this is to conclude our lesson, which was about the dynamic IPv6 dynamic routing protocols. Hope you get full idea about these three protocols, and see you in the lab exercise. Thank you very much for watching.